So what do we notice? What do we notice about this thing? Just tell me what you see. It's relatively the same, isn't it? So each outcome is relatively the same, okay? Now, in actual fact, if you look at the raw probabilities, they're a little bit off, okay? So the first one is like 16%, then 16%, then 17% for a 3, 15% again for a 4, 16 or 17% for a 5, and about 19% for a 6, okay? Now, what do we expect the probability to be? So what's the probability of rolling a 1? Sorry?
16.6 or 7.
Yeah, perfect. So probability of a side coming up should be 1 in 6, which is 16.67%, isn't it?
Yes.
Yeah? So that's what we're expecting. Now, we would call this a theoretical probability. Because we're basing it on theory. We know the formula for probability is just simply the number of favourable outcomes divided by the total number of outcomes. Okay? We can assume that these are fair dice. Okay, they are fair dice, means that each outcome is equally likely, right? And we know that it should be 1 in 6, which if you convert that to a percentage is about 16.7%. Okay? Have a look in here though. Are there any in there which are 16.7% exactly? No, okay? There's some which are around 16%, but look at that probability of a 6, for example. That's way higher. It's closer to 20%, right? So what we would call these, do you know?
Experimental.
Good. We call them experimental probabilities. Okay? And that is just simply worked out in the same kind of way. So we said, well, the probability of finding an outcome, so probability of getting a side, should be the number of times that side came up divided by the total number of throws. Okay? So we did it through experiment. Now, if you didn't know theoretical probability, so if you didn't know the total number of outcomes, and if you didn't know the total number of times that side should come up, then you could go to experimental probability. Another way of calling experimental probability is empirical. Okay? So empirical or experimental, it literally means the same thing. Literally means you go out, you do an experiment, and you're able to work out what you need. Okay? Now actually in this case, you look here, we can see something going on. They're about all the same, but the only trouble with experimental probability is it's not going to be exact. It's not going to be exact. There's always going to be a little bit of variation. Because, I don't know, perhaps some people throw the dice in a particular way to make sure that it doesn't sort of land in a particular way, yeah? Which, again, has an impact on those probabilities. Does that all make sense? Yeah? So, in actual fact, experimental or empirical probabilities aren't necessarily going to be that reliable. But how could we improve the reliability of this?
Increase the times we experiment.
Absolutely. If you increase the sample size, it should be the case that the experimental probabilities should approach the true theoretical probabilities. Now, we call this a really important idea. So as we increase the number of throws, so let's say n is the number of throws, and we increase it, so we say it approaches infinity, it gets bigger. Okay? The experimental probabilities, or the empirical probabilities, should approach what's happening in theory. Okay? Now, this is a really central idea. We will meet it again. It's something called the central limit theorem. It simply says that as you increase your sample size, the experiment will approach what's actually happening at the true population level, the true theoretical level. So the central limit theorem. Is that okay with everyone? Yeah? Okay, so this is effectively the graph which we got in Excel. Okay? This is effectively our probability mass function here. Okay? Now, could you describe this probability mass function to me in words? What do you see? Go on. So it's the theoretical probability, and the theoretical probability of each outcome is the same. Absolutely. Okay? Now, how could I write this as a function? So you've told me that the probability, so the outcomes 1, 2, 3, 4, 5, and 6, all have a probability of a 6. They're all the same, okay? and you've also told me that the probability is 0 for all other values, so for all other outcomes. How would you write this as a function? Now, I see some of you got the slides open already, but how could you write this as a function? So here's my probability mass function, which I want to write, f of x, that's my probability mass function. How would I write that? How would I write those two sentences there as a function? In other words, using algebra and things like that.
Less or equal of 6.
Okay. So you're basically saying for the outcomes, let me get rid of this.
X is equal or less.
So x is less than or equal to 6, right? Should be equal to a sixth. But then surely if x is less than or equal to a 6, is equal to 6, surely that should include things like 5.5 and 2.7. Right, so you need to be a little bit more specific. Here's how I would do it. Okay, so f of x, remember, is probability that x is equal to some outcome. So there's two options here. Either the probability is 1/6, so the probability is 1/6, or it's equal to 0. Those are my two options. One or the other, 1/6 or 0. Okay? What are the conditions if the probability is a sixth?
X equals to 1, 2, 3, 4, 6.
Good. 1, 2, 3, 4, 5, or 6. Good. Otherwise, it's equal to 0. Yeah? Because any other outcome of x, any other value of x, has a probability of 0. Like 2.7 is not an outcome, I know, therefore it has a probability of 0. It can't come up. An outcome of 7 is not possible, therefore it's got a probability of 0. Does that make sense? Yeah? So, we would call this a piecewise function. Literally, it's broken into pieces. Does that make sense? Yeah? Now, in actual fact, you can have as many pieces as you want to this function. Have as many pieces as you want. In this case, I've just got 2. It can either be a sixth or 0. There's only two outcomes there's only two probabilities that can happen. So we call this a piecewise function. Okay? Now, in actual fact, when we have lots of outcomes, so these outcomes here all have the same probability. They're 1/6. Otherwise, it's 0. Okay? When we have that condition, we give that distribution a special name. Do we know what we call it? So if all outcomes are the same, it means that they are united or they are uniform. They have the same shape. Okay? So this would be called a uniform distribution. So literally, just to re-emphasize, the conditions for a uniform distribution is when lots of outcomes have the same probability. So here we go, 1, 2, 3, 4, 5 or 6 all have the outcome of 1/6. Okay? Otherwise it's 0. So when we have a situation where outcomes all have the same probability, we call that a uniform distribution. Is that okay? Good. Okay, could you have a go at this for me? So now we've got, I've used the theoretical probabilities here because actually let's assume we've done this enough times so our empirical probabilities approach our theoretical probabilities. Could you find for me the table which describes the cumulative distribution function, the CDF? And then could you have a go at plotting the graph for that CDF for me? Okay, so what would f of 1 be equal to? 1/6. What would f of 2 be equal to?
1/3.
Yeah, or 2/6. Let's keep it consistent. Yep. What would f of 3 be equal to? 3/6 or a half. What would f of 4 be equal to? 4/6. And f of 5?
5/6.
And f of 6? Yeah, 1 or 6 over 6. Good, exactly. Okay, so we basically have these probabilities. All that's happening here, just adding together consecutive probabilities up to that point. So, for example, what would f of 2.7 be equal to?
2/6.
Absolutely, yeah? 2/6, okay. What would f of 0 be equal to? 0. What would f of 8 be equal to?
1.
Yeah, because it's adding together all of the probabilities which are smaller than or equal to 8. Last time I checked, that's 1. Yeah, good. So, if you were going to plot this, you don't have to. If you're going to plot this, you get this staircasing fashion. Okay? So, in other words, the probability stays at 0 until we hit the first outcome, which is 1. then it increases to 1/6, okay? And then it stays at 1/6 until we hit the next outcome, which is 2, and then it increases to 1/3 or 2/6, and then it stays at 2/6 or 1/3 until we hit the next outcome, and so on and so on and so on. And actual fact, for every outcome above 6, the cumulative distribution function, or f of that value, will be 1. Does that make sense to everyone? Yeah. Good.